everybody, and welcome back. This is part 2 of energy and enzymes. And when we left off, we were looking here at the evolution of more complex organisms. Doesn't violate the second law of thermodynamics. And really what we're saying here is that when things become more complex, when they become more ordered, we are decreasing entropy. But, sometimes we might think, well, doesn't that violate the second law of thermodynamics if we're making things more ordered over time? That's actually not true, because when we make things more ordered, what happens is that in order to make things more ordered, we have to increase the disorder of the total universe. So we have to, in order to get the energy to order things, we have to break down other things. So ultimately, the universe becomes more disordered when we make things more ordered. So we are going to be talking about chemical reactions for part of today. And chemical reactions, as we know, deal a lot with energy. Some chemical reactions release energy. We call these reactions exergonic. You may remember from chemistry calling them exothermic reactions. Exergonic reactions are referred to as spontaneous because they can occur without a big net energy input. And usually these exergonic reactions are going to be involved in breaking down or digesting polymers into smaller pieces. So exergonic reactions would be hydrolysis, and as we talked about before, catabolic reactions. All right, so we are digesting molecules, we are creating less organization, therefore we are doing what with entropy? We are increasing entropy because we are creating more disorder. Meanwhile, some chemical reactions require an input of energy. These, like exothermic in chemistry and biology, we're going to call that endergonic. We're going to be building, so we're going to be making things bigger, making big chains of polymers. And this is going to be a synthesis reaction, and that is an anabolic reaction, right? So this time, as our penguin tells us, building molecules is going to result in more organization. So what's happening with entropy here? Entropy must be going down because we're creating more order. Here is an example of an exergonic reaction. So notice the energy level of the reactants, and then notice the energy level of the products. The products do not have as much energy as the reactants. That potential energy is lower. Where did that energy go? Well, that energy couldn't just disappear. It had to be released into the environment, probably as heat. So energy is released. This is probably a digestion reaction, so we have a bigger molecule breaking up into smaller molecules. And negative delta G, the delta G refers to as you can see that here, the change in free energy. Free energy is the energy that's available to do work. So basically, by undergoing this reaction, we have released energy, and some of that energy, it is possible to capture it and to do work with it, with that released energy. So that is a negative delta G. Energy is released, so something else can take it and use it to do work. That's important. We also want to note that we are increasing disorder by releasing this energy. The products are at a lower energy state, and therefore things are less ordered. Okay, here's an endergonic reaction. An endergonic reaction, again, compare the reactants to the products. The reactants have less energy than the products. Therefore, we had to gain energy to make this happen. Energy got invested, and this would be a building reaction like synthesis. So where did this energy come from? Energy had to be supplied. Well, it had to come from free energy that's floating around somewhere. It has a positive delta G because we have to supply free energy, energy that is available to do work. So if you notice, these two are inverse of one another. One releases free energy and one requires free energy. All right. Here we have more examples of exergonic and endergonic reactions. Exergonic reactions are going to release energy and create disorder. Notice how this polymer is broken down into monomers. And then here we have an endergonic reaction. Energy had to be supplied, and we have created more order by making something more complex. All right, so where does this energy come from? If we are trying to build something, if we're trying to make things more ordered, we need free energy. Where is that free energy going to come from? Well, we're going to couple an exergonic reaction with an endergonic reaction. So take a look at how that might work. Here's a digestion reaction. It's going to release a bunch of energy, negative delta G, free energy. Some of that energy is available to do work. A synthesis reaction could utilize some of that free energy in order, to make a polymer. So in order to build something, we've got to break something down first. Well, one important thing that we use to couple reactions is called ATP. ATP is the energy molecule in cells, and it is the molecule that couples reactions together. ATP has an adenine, it has a 5-carbon ribose sugar, and then it has, most importantly, 3 phosphate groups. The bonds between the phosphate groups are high energy bonds. So right here where I'm pointing at, this is the highest energy bond in ATP, and this is also a high energy bond, but not quite as much. These bonds between phosphate groups are important, right? Think of them as like loading a spring. Each phosphate is negative. So we have 3 negative things attached to one another. Do negative things typically attract one another, or do they repel? We know that the negatives repel. So these phosphates are like a loaded spring. If they're together, they're very, very unstable, and those phosphates want to pop off and break that bond. So we have an unstable molecule that has this loaded energy, like a charged battery or like a loaded spring. These phosphates want to be removed. There's a video on the topics page that you can watch about ATP to kind of help you understand. So ATP is an energy carrier molecule, a molecule that temporarily stores energy in bonds. So what happens? Well, an energy carrier molecule, as it says on the right, picks up an energy charge from an exergonic reaction. Then it carries it, so it takes free energy from an exergonic reaction, carries it somewhere else, and then it's going to release that energy to drive an endergonic reaction. We see that happening here. We have ATP, those spring-loaded phosphates. Those spring-loaded phosphates are going to release energy eventually, and they will drive an endergonic reaction. So if you want to build starch, ATP can help do that. Meanwhile, what's left of the ATP? Well, the ATP fell apart. It became ADP. The D stands for diphosphate, or 2 phosphates. And then we have that third P. It's just floating around. It's not attached to the rest. So then what we can do is we can take the energy from an exergonic reaction, like breaking down glucose, and that energy can be used to attach that last phosphate back on the molecule, spring loading it, like you're like loading a spring, right? Charging a battery, and then that is going to make ATP again. So I like to think about ATP as a charged battery and ADP as a only partially charged battery, not quite as much energy stuck in there. Okay. ATP is continuously formed and it is continuously broken down. ATP gets used very, very quickly. So ATP is continuously formed and continuously recycled. We constantly have this recycling of ATP. Therefore, it's a short-term energy storage molecule. We would use ATP pretty quickly. So if you wanted to store some energy, ATP is not the way to go. It gets used too quickly. Instead, you would want to store energy as sucrose or glycogen, maybe starch, or if you really wanted to store it for a long time, you maybe would want to store it as fat. All right. There are other energy carrier molecules as well. There are energy carrier molecules that are electron carriers, and we are going to get to this next time. So we're going to stop at ATP, and we're going to continue this with the next video. So stay tuned and let me know if you have any questions.